Hi. Today you can tell by the lesson title that we're going to be solving exponential and logarithmic equations. Actually, we're going to be using those kinds of equations for a couple of days. Today we'll look at 4 methods or techniques for solving them. Tomorrow we'll look at applications that use those techniques. So let's begin with the first of our 4 methods, which says that you should express each side as a power of the same base. Well, that doesn't sound too bad. The logic of that is here. It says if b raised to the mth power is equal to b raised to the nth power, well, that would kind of lead you to think that m must be equal to n. And that's the algebra that we're going to be using, the logic we're going to use. So the first thing to do would be to rewrite both sides as powers of the same base. Rewrite both sides as powers of the same base. Well, that doesn't sound too bad. We're going to see a couple of example problems in a moment. If you look down at this one, that 125 can be expressed as a power of 5. So that's going to be our first step in solving that one. Next, it would be set the exponents equal to each other. So once you have them both powers of the same base, set the exponents equal to each other and then solve for the variable. So let's see how that plays out down here. Alright, 5 raised to the 3x minus 6 on this side. Well, 125 is a power of 5. In fact, it's 5 to the third power. So I have both sides written as powers of the same base. My next step is to set the exponents equal and then solve for x. So 3x minus 6 must be the same thing as 3. And you can see that's just the truth. If the bases are alike, then the exponent, so if these things are equal and they have equal bases, the exponents must be equal. So let's solve. Let's see. Add 6, so 3x would equal 9, and x will equal 9 divided by 3, or 3. That works for me. You should, folks, I hope you will, check your answers tonight. I'm saying that if I take 5 and raise it 2, and then I'm going to do a little math here. 3 times 3 is 9. 9 minus 6 is 3. 5 to the third ought to be the same thing, and we know it is, as 125. So we checked our work, and that's not a bad idea today. This one doesn't look quite as straightforward. However, if you think about it, both 8 and 4 are powers of 2. So let's see if we can't write that 8 as 2 to the third. And that exponent x minus 2 was already there. 4 is 2 squared, so 2 times that exponent that was already there. And now we do have powers of like bases. Both bases are 2, so we should be able to set the exponents equal to each other. And I'm going to distribute as I'm talking here. So 3 times x minus 3 times 2, so minus 6, has to be the same as 2 times x minus 6. I think I see where this is going. Add 6 to both sides. 3x is 2x. Subtract 2x from each side. Then x will equal 0. And yeah, I think that's the only way that that could happen. So we set those both sides of the equation as powers, or we wrote them as powers of the same base, and then we just did the arithmetic with the exponents. So that's kind of a cool method. Of course, it's not going to work every time because not each equation has sides that can be set as powers of the same base. So we need other strategies as well. And this is the next one we're going to talk about. That is, we can solve exponential equations by taking the log of both sides. So take the log of both sides, and of course that could be the log or the natural log. Then it's use the power rule if necessary. That is, you might have to bring an exponent out front. Solve for the variable. And lastly, use your calculator on the final step. Okay, use the calculator to approximate your answer. See, what's going to happen with these things is we're going to get answers that involve log expressions, like log of 6 over log of 2. Well, I don't know what that is. So I'm going to use my calculator to approximate. However, I'm only going to do that at the very last step. The only place I want to do any approximating is at the end, so that I can round to the nearest tenth or hundredth. And that's as a final step. All right, let's see how that would work here. Well, it says you take the log of both sides. So log of 5 to the x equals log of 134. Again, what you do to one side of an equation, you must do to the other. So you take the log of both sides. Power rule will apply here, that x can come down in front, and so we would have x times the log of 5 equaling the log of 134. And you know exactly where this is going. We need to divide by the log of 5 if we're going to get our x. X will equal the log of 134 divided by the log of 5. And now is the time to use the calculator. We want to know about what that number is. So log of 134 divided by log 5. Right around 3.04. So around 3.04. Now notice, rounding to the more decimal places you keep, the better your approximation will be. In fact, I know if I had rounded to the whole number and said that 5 to the third is 134, I know that's not right. 5 to the third is 125. So you need to keep some precision in your answers here. It's not bad to go out to the hundredths place. In some places they'll recommend that you go out to the 4 places past the decimal. So they would maybe say go 0432 here. The more precision you keep in your answer, the better, usually. So here's another problem that we're going to use the same technique with. And folks, even though this has an e in it and the exponent is a variable, it's still just an equation. The good rule of thumb is to get that term with the exponent as isolated as you can. So let's add 5 to both sides and then divide by 7. So 7e to the 2x is going to equal 5 plus 58, which is 63. Dividing both sides by 7 would get us this. E to the 2x equals 9. That's looking a lot better. Power rule, well, actually we're going to take the natural log of both sides, and the power rule will apply here. So it's going to be the natural log of e to the 2x equals the natural log of 9. And let's see, power rule. So 2x comes out to the front, and then I remember, hey, the natural log of e is just 1. So that 2x is all by itself over there. 2x is equal to the natural log of 9. Right? That was handy to recall, that the natural log of e is 1. The power that you raise e to get e has to be 1. Now our x is going to be, according to this, the natural log of 9, which I do not know, divided by 2. I am thankful, however, that my calculator does know. So I tell it, find me the natural log of 9 divided by 2. And it says that x is around 109, or about 1.1 if we went to the hundredths place. All right, good. We could try that again, and I hope that you will as you're working. However, this is the third time I've got this answer, so I know it's right. The last of these problems looks a little bit more complicated than the other, and it is. Okay, we've got exponents that contain variables on both sides, and we are non-equal bases. So we're going to have to do a little bit of legwork on this one, but let's start by taking the log of both sides. And I know the power rule is going to come into play, so I'm going to go ahead and put that exponent out in front to begin with. So 2x minus 1 times the log of 3 equals, same thing over here, I'm going to put x plus 1 out in front, whoops, x plus 1, times the log of 7, to get the log of both sides. I see x on both sides still, and that's not looking a lot better to me right now, but I do see that this would be a distribution. Even though it says log 3, it's just a number, folks, and it can multiply just like any other number. So let's distribute. We're going to have 2x log 3, and then negative 1 times that, so minus log 3 equals, and over here it would be x log 7 plus 1 times log 7, which just is log 7. Okay, now things are looking a little bit better to me. I have terms that have an x on both sides and terms that don't have an x on both sides. I'm going to get my x's together. So I'm going to subtract this term. I'm going to add that term. So I will have 2x log 3 minus x log 7 equals, and now I'm adding this, so log 7, which was already over there, plus log 3. Okay, well that's good. These terms both have an x in them, so I could factor that x out. And there's a little bit of algebra going on in this problem. If I divide this term by x, what's left behind is 2 times the log of 3. If I divide this by x, factor that x out of there, I'm going to be left with a log 7. And on the other side, I'm just rewriting log 7 plus log 3. Now, if you look at what we have, these are joined by multiplication, x times that whole thing. So if I want x all by itself, I have to divide by that long thing. So I'm going to take the log of 7 plus the log of 3 and divide that by 2 times the log of 3 minus the log of 7. And I put the parentheses because I'm going to come over here to my calculator, and I like to put things all in at once. So I need to divide everything that's on the top. That's why the parenthesis is necessary. Log 7 plus log 3. Oops, I forgot to close that parenthesis. Plus log 3. And that needs to be divided by, and now I'm going to open a parenthesis for the bottom. 2 log 3 minus log 7. Good. Putting things in all at once is a wonderful tool if you want precision at the end, right? The calculator is going to do the estimating right now. The only thing is you have to be aware of where you need parentheses, so be careful, but that definitely, I like to enter things into my calculator that way. I guess I better hit enter so I know the answer. All right, right around 12.11 is the value of x that makes this equation true. Very good. So our two methods for exponentials were trying to get things to be powers of the same base, or taking the log of both sides. Those are our two exponential strategies. Let's take a look at the two logarithmic strategies next. This one says that we should use the definition of logarithms to solve logarithmic equations, and you can use this method, folks, when there is only one side with a log expression. Okay, so a four-step strategy again. I like steps, as you know. And the first step is simplify to get to a single log expression if you need to. And you can see that on the left problem down here, that's not going to be a deal. This is only just one log expression. Over here, we have to change this so that we get exactly one log expression, so we'll condense a little bit there. Simplify to get a single log expression if necessary. Once you have that, rewrite that logarithmic thing as an exponential. That is your applying exponential. You're applying the definition of logarithm. So when we get down here, we're going to say, okay, you look nasty to me, but I know that what you're really saying is 2 to the third equals x minus 4. We're going to rewrite it as an exponential. Then it's going to be solve for the variable. And just remember, the last line is here to ask you to check your answers. Remember, you cannot have any negative numbers as an input to a log expression. We need to check our answers carefully because you will remember the domain for logarithms is positive. So only x's that will create positive arguments are allowed here. So you check your answers. Only x's that give positive arguments are allowed. So if you come up with numbers that will make, say, the argument in a logarithmic expression equal to something less than 0, that's not going to be okay. Check answers. Only x that give positive arguments are allowed. And the argument is not somebody that's trying to pick a fight. Argument is this part of the log expression. Okay, so let's see. We simplify to get a single log expression if necessary. Not necessary here. Rewrite as an exponential. Okay, so that's applying the definition. And you will remember that this is saying the power that you need to raise 2 to in order to get x minus 4 is 3. That is, the log is the exponent. So 2 to the third power is the same thing as x minus 4. Well, that's kind of nice because 2 to the third is 8. And if that's x minus 4, then x must be 12. Okay, that's a nice little solution there to that. That looked kind of daunting at first, but really it's not. On this second example, we do have something that's got 2 logs in it in 2 places. We want just one, a single log expression on one side of an equation. So this is broken out, is what I say, or expanded with an addition. So that means that it's going to condense as a multiplication, or we can rewrite this as being this. The log of, and it's going to be x times x minus 3 equals 1. Now we can distribute here. So the log of x squared minus 3x equals 1. And now we rewrite. We're on the second step because we've done this. Now we're here. Rewrite as an exponential. What's the base of this log? Well, none was given, so that's a common log, base 10. So we would write 10 raised to the first power is the same thing as x squared minus 3x. And this is going to be a quadratic, no way to get around it. So let's subtract that 10 from both sides. X squared minus 3x minus 10. Think x. You don't need the box here because you got a number that's a coefficient that's 1. Got to multiply to make negative 10. We have to add to make minus 3. Yep, I think negative 5 and 2 will be our guys. So 0 is equal to x minus 5 times x plus 2. The x's that we would get from there, set each parenthesis equal to 0. This one would give us an x of 5, which is good. This one would give us an x of negative 2, which is not, right? You can't have the negative 2 wouldn't work there or there. So that negative root was extraneous. We just can't use it. It's not part of our solution set. So there's a way to solve logarithmic equations. That's pretty cool. Our fourth strategy says that it's very similar to the first one we looked at. This says, though, the other way. Express both sides as logs of the same base. So if you can get both sides to be logs of the same base, then it makes sense that the arguments m and n must be equal. If this expression equals this and they're both to the same base, m must equal n. So what we want to be able to do is get both sides as logs of the same base. We want to set our arguments equal. The argument is this part. We want to solve for the variable. And we are going to remember our same caution that we had last time. Values of x that make the argument negative are no good. Yep, you just can't have them. So I'll just say won't work. Okay. All right, values of x that make the argument negative just won't work. All right, we have natural logs here. So e is the base here. Here we have two expressions, so we need to get this simplified a little bit. Let's just rewrite this side. The natural log of x minus 3 equals, and now this is expanded as a subtraction, which means it condenses as a division. So it's going to be the natural log of this guy on top, 7x minus 23 over x plus 1. Alright, now we do have logs of the same base, so we can set the arguments equal to each other. X minus 3 will equal 7x minus 23 all over x plus 1. X is everywhere here. This is not going to be pretty, but let's multiply both sides by x plus 1. So we're looking at x minus 3 times x plus 1 equaling 7x minus 23. Now we need to multiply quantity times quantity, so you'll either use the box method or FOIL, and you know I'm going to like FOIL, so I'm going to say x times x is x squared, x times 1, 1x, here's minus 3x, that's a total of minus 2x's, minus 3 times 1 is minus 3. You know what? That square's not going away. Let's just subtract the 7x while we're at it and add 23. So we get everything over on the same side. X squared minus 2 minus 7. X squared minus 9x. Negative 3 plus 23 is plus 20 equals 0. Boy, it'd be nice if that factors. Can you guys think for me real quickly? 1 times 20 is 20. We need numbers that multiply to 20 but make negative 9, and I will bet that you are already there. I'm thinking negative 5 and negative 4. So let's see. X minus 5 times x minus 4 equals 0, and that means that x is either going to be, so set each one equal to 0. X is either 5 or it's 4. We must check those and make sure that they'll be okay. Back in our regular first expression, 5 minus 3, 4 minus 3, both of those are okay. 7 times, that's 35, or 28, that's okay. And here we're good too. So our last equation has two possible answers. X could be 5 or 4. And ladies and gentlemen, that's it. We've looked at 4 strategies for solving exponentials and logarithms. I'm going to ask you to get out there and try that. You try it as soon as you hope that you have a wonderful night tonight.